This is Mesut Şahin from Math Department. We'll talk about continuous functions. So we have seen continuity at a point. Now we talk about continuity on an interval. We say f is continuous on the interval I if it is continuous at every point of the interval. In particular, we say f is continuous in absolute terms if it is continuous at every point of its domain. For instance, the function 1 over x is continuous on its domain because the function is not defined at 0, which is a real number. But for us, since 0 is not in the domain, this is not a problem. So we regard this situation as nothing opposed to continuity of the function. So we regard 1 over x to be a continuous function in result. There are lots of continuous functions. For instance, all polynomials are continuous because they are defined everywhere and their limits coincide with the values at the point. So they are always continuous. But for the other functions, we have to check that they are defined in order to talk about whether they are continuous or not. So the claim is that all these rational functions, rational powers, all these trigonometric functions, and absolute value function, they are all continuous as long as they are defined on an interval. The next theorem gives a way to construct new continuous functions out of two continuous functions f and g, namely basic arithmetic operations like summing two functions as in the first item or taking differences will produce new continuous functions out of two continuous functions f and g. Similarly, the product of f and g is a continuous function. Constant multiple of a function is continuous. The quotient function f over g is continuous, provided that the denominator g is not 0 at the point c. Nth root of f, or f to the power 1 over n, is continuous, provided that fc is positive when n is even, and there is no such condition when n is odd. So another way to obtain continuous function is to compose two continuous functions. Suppose f composition g is defined on an interval containing the number c, and if f is continuous at L and limit of g at c is L, then limit of the composition f composition g is nothing but fL, which is also f of limit of g at c. And this is because limit of fy when y tends to L is fL, but L is also the limit of y when y tends to L. So in other words, continuity of f at L means that lim part of this expression can enter inside the function f, as in here. So continuity of f means this one. So if we apply this fact here, we understand why this statement is true. Because this is gx is regarded to be y, and limit of gx will be L. This is the assumption. If limit of G is L at C, then limit of the composition is going to be FL because of this reason. And in particular, if G is continuous at C, namely GC is also L, then the composition FOG is also continuous at C because this limit will be FL and L is GC. So, by definition, composition function will be continuous at C. Okay, there are lots of continuous functions as you can see from this example. For instance, in item A, you see a polynomial which is continuous everywhere. And in item B, you have a rational function x minus 2 divided by x squared minus 4. And this is continuous everywhere except at x equals minus 2 and x equals plus 2, making denominator vanish. And absolute value function, which is a composition function of absolute value function and the polynomial x squared minus 1, since they are both continuous everywhere, the composition is also continuous on real numbers. And domain of square root of x is the set of all non-negative real numbers. So this function is continuous everywhere on its domain. Similarly for the others. So these functions, composition of a polynomial, quadratic polynomial here, and square root of x function, the composition is continuous whenever it is defined. And the function in item F is the absolute value of x divided by square root of absolute value of x plus 2. It's a ratio of two functions, and absolute value function is defined everywhere and it's continuous everywhere. And denominator square root of the absolute value is defined whenever x is not minus 2. So when x is minus 2, the denominator vanishes, so the function is not defined, except at minus 2 it is always defined, and you get a continuous function because absolute value is never negative. Okay, so sometimes a function is not continuous, but there is a chance to make it into a continuous function, and in this case we get a new function written in capital F, and we say it is the continuous extension of the previous function. So here is the situation. So if the function f has a limit at c, but fc is not defined, so f is not defined at c, then you can define a new function, capital F, by declaring that capital F at C is the limit L. So if you declare the value of capital F at C to be the limit of the previous function f, then you have a new function, capital Fx, that is continuous at C. So this new continuous function is an extension of the previous one, which was not continuous at C. So let's look at this example. So you have x squared minus x divided by x squared minus 1. Say this is fx. Let's show that it has a continuous extension to x equals 1, and let's say what the extension is. So So if you look at the sketch of the graph, you see that the function is not defined at 1 simply because x squared minus 1 is 0 there. So the denominator is 0, so f1 is not defined. So there is a gap here, making this function discontinuous at 1. But if you think about it, x divided by x plus 1 and our function fx coincide at other values. So if x is not 1, there is a cancellation here, x minus 1 and 1 factor of x squared minus 1 will cancel each other, and we will get x divided by x plus 1 here. So capital F and the original f is the same everywhere except at 1. What is nice about capital F is that it is also continuous at 1. So capital F1 is 1 over 2. And if we think about graph of capital F, we see that this gap is filled with this dot so that we have a continuous function. So the new graph is the graph of capital F, which is continuous everywhere except at the origin, except at minus 1. So this is still not continuous at minus 1. Okay? So capital F is continuous on its domain, and minus 1 is not in the domain, so it's not continuous at minus 1. Okay, so the original function has a continuous extension to x equals 1, but it doesn't have a continuous extension to x equals minus 1. Both capital F and the original f doesn't have a continuous extension to minus 1. So we can't remove the discontinuity at minus 1. So in order to show a continuous extension of this function sine theta divided by theta, we first need to obtain its limit. So we first prove that limit of sine theta divided by theta is 1, and clearly this function is not defined at theta equals 0, so it is not continuous there, but we will see that there is a continuous extension of this function to theta equals 0. So let's prove this first, and so as to prove that limit is 1, we first look at this picture here. There are three areas to compare. So the first one is the smaller triangle AOP, whose area is the length of the base, which is 1, times the height, which is sine theta, divided by 2. So this is the area of the triangle AOP. And then we have this sector of the circle, whose area is theta divided by 2. And finally, we have the biggest triangle, whose height is tangent theta, whose base length is 1. So 1 times tangent theta divided by 2. So this is the third area. So we have these inequalities. Now if we divide by sine theta divided by 2, we get this inequality, 1 smaller than or equal to theta divided by sine theta, smaller than or equal to 1 over cosine theta. Now if we take reciprocals, 1 will become 1 over 1, which will be the biggest number among all. And theta divided by sine theta will become sine theta divided by theta, which will be the second biggest number. And 1 over cosine will become cosine theta. So we have this inequality now. And we know that limit of cosine at 0 is cosine 0, which is 1. So we have this limit to be 1 by using the sandwich theorem. So this part goes to 1, this part is also 1. So the function between them must go to 1 as well. Okay, so sine x divided by x function has a limit 1 at the origin, but the function is not defined at the origin. So this point, there is a gap here at 0 in the function, in the graph of the function sine x divided by x, but we can fill in this gap by declaring that capital F takes the value 1 at 0. So if we fill this gap by declaring that capital F0 is 1, which is the limit of sine x divided by x at 0, we obtain a continuous function. So this new function is continuous at 1, at 0. So capital F is the continuous extension of sine x divided by x. Thank you for your attention, and you can contact me from my email address.